the main topic, really the topic of this talk is going to be about revisiting reinforce, which is an old school reinforcement learning optimization algorithm and repurposing it for RLHF of large language models. I did this work as a part of my, I was in a residency program in Cohere for AI, called the Research Scholar Programs. And this was my, towards the end of my term there. And it was a joint between Cohere for AI and Cohere. You've probably heard of a bunch about, learning from human preferences, RLHF, preference optimization, offline, online algorithms, or rewarding language models. Really, at their core, all these algorithms, they boil down to learning from a preference function, in this case, human preferences. Basically, by a preference function, I mean, some black box thing that you give it an input, and then it says whether it's preferred by humans or whatever entity or not. Now, RLHF, using reinforcement learning in this context, was actually the first framework to sort of align language models to such preference functions. And canonically, they use, when it was first introduced by folks at OpenAI, they use Proximal Policy Optimization, PPO, which you might have heard of. It's an algorithm directly taken from the RL toolbox and just sort of slapped on RLHF. It sort of stuck, upon its introduction into RLHF, no one really questioned its use as the RL method, even though there have been things that methods that do not have the explicit components of reinforcement learning. At the core of this work, what we questioned was, is the reputation and popularity of PPO merited? And we sort of dove into, under the hood, does it make sense to use PPO for language models? So just some quick background on reinforcement learning from human feedback. Typically, it's done in 3 stages. The first stage is where you do instruction tuning. This is like your traditional instruction fine tuning, where you align a pre-trained base model to follow instructions. You typically just use a normal cross entropy or log likelihood loss with a prompt and given instructions in the data set. And then once you have this SFT model, you use it for 2 things. The first thing is you use it to train a reward model on top. You use it as the initialization of a reward model. The most common way to actually train this reward model is through binary classification in a way. You use negative log likelihood again, but then what you try to do is you have a data set of preferences where you have a prompt and 2 completions, and one completion is preferred over the other. And the annotation or the label is either done by humans, or you can use other language models as well. But at its core, it's really a binary classifier that you're training, and then you take the super last scalar in the model as your reward. Once you have this reward model, you have your policy, I guess, as we call it in reinforcement learning, or your generative model that you care about actually aligning. What you initialize it from the SFT checkpoint that you got in step 1, and then what you really try to optimize is you try to maximize the reward as outputted by the reward model. So, but also you don't want it to move too far away from its pre-trained or / instruction fine-tuned reference point. Because if you optimize too much this notion of reward or preference, you tend to reward hack, which means you find gaps and things within the reward model that that the language model can actually abuse and hack the reward model, but it's not actually good, but it does not actually lead to good completions. That's why you have a penalty, a divergence scale penalty divergence in the actual optimization objective, which is also here. But yeah, at a high level, you want to optimize towards the reward, but then not too much, such that you forget things like basic English or become incoherent. That was sort of, like super quick run through the RLHF pipeline. But then you have PPO, Proximal Policy Optimization, which is directly, as I said, taken from the reinforcement learning toolbox. And by reinforcement learning, I mean deep RL, where you have, Atari or other game environments. Originally, when it was proposed to stabilize learning in deep RL. Deep RL is known to have high variance, and it's just super unstable. And that's why within PPO, there is a couple of actually let's say, countermeasures against large gradient updates and just high variance dynamics in your training. But it requires training and maintaining an additional network in memory. And it also has a couple of components in its loss. You see the loss at the very bottom. It looks pretty complicated because it is. It is actually pretty complicated. So for the typical practitioner, it's actually not an extremely difficult thing to tune. And RL is also known to be finicky, and PPO doesn't help that. It just adds on top of it. So the main goal, I guess, was to pick apart PPO, see which components are necessary, which are not, and then based on those insights, propose something new. Before PPO, there was Reinforce, which was by Williams in 1992. I think that was published around 30 years ago, and it's really the backbone of everything in RL because it's really how you define a gradient update rule such that you can maximize the expected reward or a reward given completions or given generations from a policy. In this case, the policy is just a language model, but then it's the same idea really. Reinforce is super simple, really. I mean, the math doesn't matter, but then you have a notion of also baselines, which are sort of like averages in a way of because this notion of reward is typically a black box function. In our case, it's a language model, but it can really be anything. You kind of want to have a sense of scale of where does my reward actually vary. In what range in a way. So you can introduce things like baselines, which are independent of your the generation you actually generate, or most of the time independent of your policy or language model. But then they reduce variance. That's the point, and they make learning more efficient. So but these ideas have been around for like 30 years. You can use things like as you're training, you just average all the rewards up to a certain step count, and then that can be a baseline, for example. So just to get a sense of like, okay, what in what area do my rewards typically fall in? This is vanilla reinforced, which has been around for a long time, and there's also reinforced leave one out, or RLOO, which is really its idea. This is the main idea behind the actual paper, in terms of the new optimization method. So it directly builds on top of reinforce, but then instead of using a baseline, for example, a moving average baseline or a learn baseline, as PPO kind of does in a way, you use additional generations from your policy/language model as a means to reduce variance. You can extend RLOO to however many samples you want, but for a given prompt, you generate K samples, and then let's say for the case of K is equal to 2. One time you you examine each sample individually and then take the other sample as the baseline, and then you take the difference. So you get terms like R1 minus R2 and then R2 minus R1 times the corresponding log probabilities. It's actually pretty simple to implement. And it also makes intuitive sense because really what it's doing is that at every single point in your training, you're generating a baseline on the fly, as opposed to sticking to baselines that are super influenced by previous gradient updates or previous dynamics in your training. So it's super accurate at the time of your training, at the time you're taking that step. This is actually super beneficial for RLHF, as you'll see in a bit. PPO reinforce RLOO, but then really PPO, I mentioned a couple of times that it's super complicated, unnecessarily complicated. You can pick apart PPO and you get to reinforce or vanilla policy gradient. So, and that's sort of the main insight that it allows that lays the basis for the argument that PPO is too complicated. PPO, it does try to address super instability in your deep RL environments, or in general in any environment. But at its core, it's an active critic algorithm where you have a policy and a value network, and the value network is similar to a baseline, and its purpose is to reduce variance in your optimization. For any active critic algorithm like PPO or A to C, the Monte Carlo estimator, or like the reinforced estimator, let's say, for your reward has really high variance. And instead of using a typical notion of baseline that I talked about before, they use this thing called bootstrapping, where they can reduce the variance a lot more than the traditional techniques like introducing baselines, but then they introduce bias into the optimization. So it's sort of like it's a variance bias trade-off again. In PPO, you have this thing called generalized advantage estimation, or GAE, which is sort of the backbone of PPO when it comes to trajectory level return estimation. And it's built in. And this GAE, this advantage estimation function, it's designed to trade off bias and variance. So, for example, you see on the bottom left, you have this hyperparameter called lambda, where as it varies between 0 and 1, and then if you increase lambda, you reduce bias, but then you increase variance. And if you set lambda equal to 1, you get something you basically get something like reinforce that I talked about before, but with a learned baseline. So it's an additional network, but then the idea is the exact same. As you see on the bottom right, the first term is the sequence level return, and then the second term is just a quantity that reduces variance. The main component of PPO that really hurts in RLHF, as we study here. So I mentioned as you increase lambda, it doesn't matter how or why it leads to this effect, but then just imagine, you increase lambda, you reduce bias, and at lambda equal to 1, you have 0 bias, but in theory, you have really high variance, which is super disliked, or you really want to avoid in traditional deep RL. And lambda equal to 0 is super biased, basically, but very low variance. Here, we just varied lambda in this range, keeping everything else the same. And the goal was to really understand, what are the dynamics in RLHF when it comes to bias and variance. And it turns out you don't want any bias. And you really, even though in theory lambda is equal to 1, has super high variance, it performs better than everything else, really. This just really means don't introduce bias at the as a means to reduce variance when you're doing RLHF, meaning you have a language model. I'll get to why this this is actually the case for RLHF specifically, whereas in deep RL you almost never want to set something like lambda to 1. You always want to have some bias, but you really want to reduce variance. There's another component in the PPO loss, which is the means of clipping. Basically, in the loss, once it just makes sure that gradients that are too big are zeroed out, because again, in deep RL, you really run into situations where you can get gradients because of this ratio or importance sampling ratio on the bottom left that are really big, and they destabilize learning. And a lot of times the policy can never recover from dips or jumps due to these oscillations in the domain, in the loss landscape. Yeah, so that's why you have clipping. Now, in practice, though, when you actually take a look throughout my training, let's say across a single batch, what percent of these loss terms at a token level were clipped? So how many times this clipping was activated? It turns out that it's not activated that much, really. It's around 0.03% or sorry, 3% of the total number of examples clipped. And if you turn off clipping, you do not lose performance, really. If anything, it increases performance. And this, again, goes directly against the insights and the findings in deep RL, in traditional deep RL. There's another sort of differentiating factor between PPO and RLOO/reinforce, as I introduced it, was that the PPO loss is token level. It's at every single token. Meaning that you get you get different gradients for different tokens. But for RLOO and reinforce, you actually treat the entire sequence as a single action, in RL terminology, whereas in PPO, you treat every single token as an action. And there's good reason why, the formulation in the context of RLHF, you're generating a completion or to an instruction, you should model it as a single action as opposed to multiple. And that's because when we train a reward model, we only attribute a reward to the full sequence. We don't have intermediate rewards that we actually care about on a per token basis. as RLHF has done, widely, let's say. The only component of reward that every token, except for the EOS token, carries is the KL component, which is not really that it doesn't really make sense at a high level. So that's why we're like, okay, if you it doesn't make sense to have every single token as an action, but then just treat the entire sequence as an action, and then that directly leads you to the RLOO and reinforced formulation, where you just have a single gradient update for the entire sequence. This is, in my opinion, the most crucial part of the actual paper, because it really explains why we observe these phenomena that directly go against all the insights from many years of deep RL, and that's really because of how the initialization of RLHF. You have a pre-trained base model that's often supervised fine-tuned. It's an unusually strong policy initialization for your policy, because your initialization is so good. You just don't have high variance. And here on the bottom left, what's getting plotted is the entropy at every single generation step. So the reason, and on the right is just trying to see, okay, how's the probability mass distributed in another way. We have vocabularies that are 56K, let's say, tokens, or even more. For example, at Cohere, it's more than 200K. It turns out that from this however many tokens in the thousands or hundreds of thousands, only less than 100 actually construct most of the probability mass when you're doing your autoregressive generation. What this means is that even though in theory at a token level you have a lot of possible actions to take, in practice your action space is actually pretty limited, because top 16, for example, you see on the bottom right. If you look at the top 16 tokens with the most probable, that are most probable, and you sum their probability masses, you basically get almost the entire distribution back. So it's it's sort of misleading to think of, to just look at the vocabulary size as a means of like, okay, this is how many actions I have, and that's why I expect high variance.
I see a question from Tatiana. When generating, do we calculate scores for each token?
Depends on what you mean by scores. If by score you mean the reward we actually optimize in RLHF, we only calculate a KL component for every single token, which is just the difference of log probability of generating that token with the current policy, and subtracting the same likelihood from the reference policy. But then if by score you mean, like, let's say a reward score, like an actual scalar that I care about when it comes to, let's say, aligning to human preference, no, we don't do it on a token level traditionally. So you take your entire generation after you're done generating the entire thing. You take the prompts, you take that generation, you put them together, you concatenate them, and then you feed it to your reward model, and then you get a single scalar. Now that single number is sort of attributed to the entire thing. It's not token level.
Please explain why in LLMs the initial policy is stronger.
We do pre-training. Pre-training is it's like usually these models are pre-trained on trillions of tokens, and that actually narrows down. It's far from a random initialization as you would have it in deep RL, because that's really the normal deep RL setting. You have a random init network, and then you have to learn to walk, or do like your traditional RL environment of like cart pull or whatnot. But here you do pre-training, and if you probably, I mean, I'd say with 99.99% confidence, if you don't do pre-training and try to do the same thing, nothing's gonna work. Or if as you get go down in terms of strength of pre-training and how much you pre-train, how many tokens you saw, these plots would shift, and that you would end up getting higher and higher variance in your environments. And you have pre-training, you also have you also have your SFT phase, which is by nature, because you do cross entropy on labels, you make your distributions super peaky. And when you make things peaky, you get plots like this where you have low entropy, because you downweigh all the tokens in the vocabulary except from your label and your SFT data set, let's say at a token level. I mean, another thing is also the fact that you condition a lot. You have a prompt. The conditioning aspect actually makes a huge difference. So on the bottom left, you see basically after the first generation, you take a plunge in entropy, and correspondingly on the right, you get a big jump in the top K probability mass. And that just points to the strength of conditioning. It's not like so like once you have the prompt and then you generate one token, you're sort of locked in a way.
I was going to ask, basically discuss this fact, which we already visited, that it's a banded feedback in the sense that we are scoring the complete trajectory and only give the reward at the end of sentence token. So I was wondering if there are RLHF methods which try to decompose this return across each token and essentially use fine-grained reward feedback instead of just getting the sparse episodic feedback in the RL training phase.
If I understand your question quickly, yes. So I mean, reinforce and RLOO are basically it's a contextual bandit problem that they're trying to solve, because you get a single reward for the entire trajectory. Now, when you do PPO, in a sense, you're trying to do credit assignment, in that you take the whole entire return of the trajectory and then you're trying to attribute it to every single action in that sequence.
Yeah, so the advantage function is doing it for PPO, and because in the PPO update step, I'm using the importance weight, which is getting clipped, like importance weight multiplied by the advantage function, which is getting clipped.
Yeah.
And the advantage function essentially is the credit assignment for each action.
Yeah.
But you could also learn an explicit credit assignment function, in the sense that if I have a trajectory with, let's say, 7 tokens, and I get a reward of 10, I can try to decompose this reward on a per token basis and say that it's a sum of 1, 3, 0, and so on for these 7 tokens. And this is basically a return decomposition function that I can train on all the completed reward scores that I have.
Gotcha. Yeah. No, that's a good question. I haven't seen any work in the context of RLHF that try to learn an explicit decomposition function to attribute rewards. But I mean, also it's like the question is, would it make sense to learn such a function? Like if for example, in the case of summarization, if I give you an entire summary, it's going to be pretty difficult to attribute the quality of the entire summary to a per token level, if you know what I mean. So
yeah.
But yeah,
I think the nuances of language versus a general MDP do
exactly. Yeah,
and that's why I was curious if there is something which tries to address the episodic feedback problem in this way.
I haven't seen any work that actually do it in that way. But yeah, that's a pretty interesting question. Yeah, it would directly be sort of go hand in hand with the arguments that I guess we're making here. So yeah,
I think so. Okay,
yeah.
Thanks.
That was sort of the build up, and now we can get into results. Because we're doing RL, and really, so you have two objectives. Everyone cares about win rate nowadays. You have your leaderboards. You have every paper cares about win rate. That's in this context. That's not the first objective, or I call that the extrinsic objective. Your intrinsic objective, which is what you optimize mathematically, is your reward, penalized by a KL, by a divergence. So here, you actually, when we're comparing different RL methods, reinforce RLOO, PPO, vanilla policy gradient, and whatnot, we care about how much they optimize a given reward score. So here, that's what you have on these plots on the bottom right. Those are how much each algorithm, given the step count, optimizes the given reward function. By the way, vanilla policy gradient is basically PPO, but then you set lambda to 1.0, so you make it unbiased, and you remove the clipping. So it's it boils down to reinforce at a token level in a way, but yeah, basically it takes the insights that we saw before and then actually applying it and making an and seeing how it works. Overall, the general consensus is that methods like reinforce with baseline, which is this baseline is the moving average baseline that I mentioned before, and RLOO outperform or basically outperform PPO, but outperform slash match vanilla policy gradient across the three settings. And the three settings are, we have two tests. There's the Anthropic helpful and harmless data set, and then there's also the Reddit TLDR summarized data set from OpenAI. And we also have two base models. One is Pythia, the other one is Llama, Llama 17B. Pythia, I think, is 6.9 billion, and then Llama 7 billion. And yeah, these are how these different plots are constructed. The unanimous sort of this thing here is that sequence level methods, basically ones like RLOO reinforced with baseline, they outperform vanilla policy gradient and PPO really. There's also Raft. Raft is reward iterated fine tuning, if I recall correctly. Their idea is, it's similar to RLOO in that you generate multiple completions, but then RLOO makes use of all the completions that you generate per prompt, your K completions. But what they do in Raft is basically they take those completions and then they filter with a reward model and they just use cross entropy. So they don't actually do RL really. It's iterative reward fine tuning. But still, it's a sequence level method. But that's the point. And it does in a way optimize a reward that it shifts your distributions to a reward. But then it's not actual RL as we know RL. Here is, I think I jumped ahead of myself last slide. But yeah, RLOO, we compare RLOO and Raft here. Again, RLOO is a thing where you extend reinforce with to multiple samples, and Raft is, again, you also use multiple samples, but then you use a filtering function really to filter out generations that don't have the highest reward score as determined by your reward model, and then you take the highest one and you do cross entropy on it. Now, actually, Raft, you could probably tell it's super inefficient compared to RLOO because it discards K minus one of the samples. Like, you don't do any optimization on top of those. But RLOO doesn't. RLOO makes full use of everything that you generate for a given prompt. And on the bottom right, you see the reward curves on the held out test set for comparing RLOO and Raft. And for a given K value, RLOO outperforms Raft, pretty unanimously. I mean, for when you do, when we train on the Anthropic HH data set on Pythia models, K is equal to 2, RLOO outperforms even Raft K is equal to 4 by a huge margin. So yeah, again, this just goes to show the sample efficiency of RLOO. And this is sort of another view of the previous plot, but then here we don't care about the actual K value. We just look at how many total samples have been generated so far, how many total completions have been generated so far, normalized, of course, by batch. But yeah, this just abstracts away the K and the K value for RLOO and Raft. But again, you see the same pattern in that RLOO just lies above Raft in terms of reward optimization, given a fixed online sample budget. And finally, probably the thing you've heard about the most, win rates. We also did, these are also win rates for RLOO, Raft, vanilla policy gradient, PPO. We also benchmark DPO. Even though it's not really RL, it's offline, but then as a means of alignment, it's definitely a baseline that we considered. RLOO beats Raft across the board for K is equal to 2 and K is equal to 4. Reinforced with baseline, which does not use an additional network, it's pretty competitive with DPO and vanilla policy gradient. For example, on the TLDR dataset, which we only train on Pythia models, it gets the highest win rate. It's pretty close, within 1% of DPO for the HH dataset on Pythia, but then it lags behind for when we look at training llama models with the HH dataset. This again also just it provides more evidence that although things like RLOO reinforced by baseline and whatnot, we provided evidence that they're good at optimizing the intrinsic objective, like the thing we are mathematically optimizing for. They're also good at optimizing the sort of hidden human preference function that typically you approximate or for with GPT-4 and whatnot, AI annotators, which is also what we use. I talked about KL before, as a means of just, you have this KL penalty in the reward, so such that, you don't forget English, or just like you stay close enough to the reference initialization. Here we compare RLOO and RAF given different degrees of KL penalization in the optimization. So beta is just a coefficient that that really determines how severely you want to penalize generations that go far from the reference policy. And as you can see, really RLOO is more robust to beta, which is your KL coefficient, compared to RAF. In low KL regimes, low KL penalization regimes, basically when beta is 0.1, 0.25, RLOO basically uses up the same KL budget, let's call it, compared to Raft, but then it just optimizes the reward a lot more. And as you continues to increase the KL coefficient, RLOO still optimizes the reward function better, but it even uses less KL budget. So as you see on the bottom right. So yeah, it just goes to show of RLOO's robustness compared to Raft. Another thing in terms of robustness is also reward noise. And here, to measure the sensitivity of RLOO and RAF to reward noise, we just artificially inject some Gaussian noise to the reward score itself, and then just run the algorithms. It's sampled from a zero mean distribution, and then here on the bottom right, we vary the degree, the standard deviation of that distribution. And yeah, again, unsurprisingly, RLOO exhibits this far smaller drop in reward optimization if you inject noise compared to Raft. And really, the reason why Raft is so less brittle compared to RLOO is because of the filtering function, and the fact that you throw away k-1 samples. Any sort of noise or any alteration in the objective through beta, for example, if you have a high KL penalty, it could significantly impact their ranking. And because you only look at the single top most sample, it's just a lot more prone to noise and gets a lot more affected by noise. But RLOO uses everything, so sort of it mellows out the effect of noise on the objective. Yeah, I think that's pretty much it from my end. In conclusion, really the two main conclusions I'd want you to take away from this is that when you do RLHF for large language models, it's not the same as deep RL. It's a different environment, it's a different setup, and you need to make different design decisions to make things work. So it's not like you can just slap on things from deep RL onto RLHF and expect them to work. You got to think about how to systematically integrate them, or if it makes sense. And there's been a whole bunch of work, starting with DPO, IPO, SRPO, whatever PO, that basically they try to take the reinforcement learning out of preference training. There has been recent ones that show that offline algorithms that such as DPO and IPO actually lag behind RLHF methods, where you actually have online generations and you penalize them in whether it be on policy, off policy. But the point is online critique through a reward model. So instead of taking the RL out of preference optimization, as you saw, if you carefully craft your RL algorithm, for example, let's say RLOO, it does lead to good performance, and you do end up outperforming offline preference optimization techniques like DPO and whatnot. That's pretty much it from my end in terms of slides, and happy to answer any questions.
This is kind of meant to increase my understanding and not getting too deep. But as I was listening to you, I was interpreting this as all the comparisons you were making were after you had trained that intermediate reward model, you call it a binary classifier. And so when you were talking about sequence level and token level, you were in fact asking, well, especially at the sequence level, you were asking that model what the reward was. And then you were using that. So you weren't basing the reward on the logits from the LLM directly in any way. You were just basically saying, here's the reward for the sequence. And now I'm going to back propagate that reward. And then all the comparisons and all the different techniques were based on that structure. Did I interpret that correctly?
That's exactly correct. So we don't explicitly optimize on the logit distributions at every token level step. We just use that distribution to get the completion. Once we have it, we're like, okay, now we have a sample completion and a given prompt. Now give me a function. This function can be anything. It can, like, I can define a function, the number of uppercase letters in a completion, and that can be a reward. And it's only, in our case, because we care about like actual meaningful alignment to human preference, we align it. We use a binary classifier, like I mentioned, that's trained on feedback from humans or something that approximates human.
I always wonder about on this RLHF, why doesn't a technique that doesn't involve that intermediate model work better? Because it seems like the same sort of differencing ought to be usable at the the LLM level when you're you could in fact look at the difference, say, between the logits of the positive sequence versus the negative sequence, and back propagate through that, just like you train the reward model. But why isn't that better? It always kind of intuitively felt like putting an intermediate model in there would somehow be worse, because there's more room for that intermediate model being bad.
Things like DPO, that's like, it's basically what they do is they skip the entire reward modeling phase, and they take the entire thing offline, and they care about the difference, let's say the logit scores between the good and bad completion, and then they do their optimization. In practice, things like that work pretty well for data sets, for academic data sets, let's say. The thing with RL is that once you have that intermediary model, you're not, there's two main things. The first thing is that you have a means of generating feedback that doesn't involve going to humans every single time. That's pretty valuable.
Okay.
Once you get to an industrial setting where I can give you a data set with 1 million prompts, and these prompts are actually for things we care about, let's say at Cohere or Anthropic and whatnot. RL is easier to scale in that sense than to going to every single going to annotators or humans to give me preference annotations for 1 million prompts. So that's thing number one. Thing number two is that things like DPO, they're fully offline, in that you don't penalize your language model you don't penalize your policy at a given time step in training according to its possible generations. In RL, because we sample at every single training step, you get this like direct feedback, really immediate feedback from your reward model that this is how you should upweigh and downweigh your logit distribution. It's sort of geared toward like the gradient updates, because they involve completions from the policy at that given time step, or in the case of PPO, like a couple time steps back. Point is, it's pretty close. That helps learning a lot if you get it right. It's hard to get right because once you do online, you run into a whole bunch of issues with compute and whatnot, compute orchestration, like how you tune it. But if you get it right, it does outperform offline things like DPO. There's, I think, the recent paper that came out from DeepMind and another one that came out from Stanford, where they sort of argue the same thing in a way that if you have things that are online, which is basically RL, you need RL for it, you outperform offline methods.
That first motivation is a little mysterious to me, because if you have so many actual training examples, human pairs, it seems like there's a certain amount of information in those human pairs, and you're sort of saying by training an intermediate model, you amplify the amount of information in there, right?
I have 1,000 or 500 human examples with pairs and annotations, but I have a million.
Yeah.
I have a million prompts. I can train a reward model with the 500 examples and then use the million prompts in RL. But with DPO, you can only use the 500 annotated examples. You can't use the prompts that you don't have annotations for.
The intermediate model somehow generalizes
Exactly.
more effectively than the LLM generalizes off that same number of examples.
Yeah.
Yeah. But okay, but it's still a little mysterious that's the case. Maybe it's just because it's a smaller model, and so it can learn faster or something. But yeah, okay. So anyway, interesting. Thank you. I have a bit to learn in this space. I was in the reinforcement space about 30 years ago, but I haven't been in that space for a while, so it's interesting. A lot of stuff.
But researchers still use the algorithm that was like available 20 years ago, right? Like, things kind of changing, but not changing at the same time.
Yeah.
Arash, maybe it's a little bit broad question, but like as you mentioned in the conclusion that like you can't just dump deep RL into LLMs. You have to consider like the specifics of LLMs. I'm just wondering what exactly you have to consider. Like, what are the specifics of using deep RL if you're applying it for LLMs?
An example, like directly taken it from the paper, is the issue of having to trade off bias and variance. In deep RL, you have to do it because the variance is so high that it breaks the learning algorithm or the learning process. But in the case of LLMs, because we talked about the initialization is so good, you have like a really good pre-trained model. The number of actions is actually in practice low when you look at the probability mass. Even though in theory you'll have high variance with no if you don't have bias, that in practice it doesn't matter. Things like that. So you don't. Another thing is having to add multiple like safeguards for instability in RL. As PPO does. You don't need those things are going to be less required for RLHF of LLMs because again it goes back to the initialization being so good. So yeah, things like that. But then I think at their core really is there's also another thing that I sort of did not mention, but it's in the paper more if anyone wants to read about it. Is that your language models? If you think of it as an environment, and then you generate, let's say, tokens, and let's say you call them actions. Your environment is deterministic in that if there is no chance of, let's say, not ending up with the how do I describe this? After you sample your token, you're guaranteed to end up in the same like partial sequence state. Like if you generate cats, you're gonna guarantee to get cats once you feed it back and you try to do the regressive generation more. It's basically deterministic how you go from a partial completion with like 10 tokens to a partial completion with 11 tokens once you have the one token. There's no stochasticity there. But you can't say the same for a lot of RL things. And that makes this problem simpler. And the fact that you also have it's a bandit problem makes it simpler. The initialization makes it simpler. So yeah.
As I understand, this our RLOO method is sort of more cost efficient compared to PPO.
Yeah.
I'm just wondering, did you guys estimate like the efficiency when it comes to cost?
No, actually, I probably should. I forgot to mention this earlier in the talk, but recently, we did a collaboration with the guys at Hugging Face, and RLOO is on TRL, and then the Hugging Face people actually benchmark RLOO against PPO, a super optimized version of PPO, and it outperforms PPO at the same scale that we studied in the paper. In terms of computation, in terms of gains, it's up to 5x faster than PPO. And it takes around a third of the memory, if I recall correctly. So yeah, like for example, I remember when I was ablating in their setup, a single PPO run with the given configuration and stuff would take 7 days, but I could do it in less than 2 days with RLOO.
That's amazing. Like, it's really like sort of game changer. Like, that's awesome.
It actually makes it pretty accessible for a lot of researchers who weren't able to do RLHF or PPO before. They could do it now because they're less bottlenecked by things like memory. And for memory, you also don't need to, because you don't need to train an additional network. You don't need to have 8 8100s or H100s to do it. You can get away with less.
I'm wondering, like, what is sort of room for improvement for RLOO, if any? Like, how would you improve it further, or like how you would, what other like steps in this kind of research work?
Yeah. I mean, RLOO it's interesting because, well, there's a couple of things. For example, you can extend RLOO to so RLOO as I currently presented it is fully on policy, and by on policy I mean you don't you generate samples from your model, you optimize on them. After you do the optimization, you generate on new samples, and then you optimize on new samples. PPO actually uses samples from previous, let's say, checkpoints of the policy throughout training. You can extend RLOO to do something similar. That's sort of what we did with the Hugging Face guys on TRL. So that's currently available. But and probably a more interesting thing is actually like zooming in on the granularity of feedback or how you get reward. Say I give you a reasoning problem or a I don't know, something that can be broken up into steps. If I can get a reward model that gives me a score for each of those steps, then I can do RLOO for at every single step. It's a natural extension of RLOO, but then that's contingent on the fact that you can construct granular level feedback.